Edexcel Further Maths, Core Pure 1 Specimen paper. This is question 8. First glance, there's a lot of words in this question. Down a little lower, we can see a first order differential equation. If you weren't too confident with working through the early sections, or if you were rushed for time, at the very least, you could jump straight in at this differential equation and solve it using one of your standard techniques. And in fact, a lot of the work of this question comes later on. So the first 4 marks are for justifying the validity of this differential equation given the description, and that involves concentration and combining rates of change. But then the second part, which is the remaining 10 marks of the question, are all for working with that differential equation, solving it, applying it to things. But we'll start at the very beginning. We'll work our way through. And the most important thing with questions like this is to identify every particular key value and variable and identify exactly how they link together. In particular, if anything talks about a rate, you want to get it clear in your head what it is a rate of and with respect to what. Generally speaking, for things like this, the rate will be implicitly with respect to time. So for instance, contaminated water pours into a container at a constant rate of 250 milliliters per minute. If you've got a constant rate, then you've got 2 options. You could either say, well, that means that we can set up a differential equation with the rate at which this happens with respect to t equal to 250, but then you could immediately solve that simply by integrating and you'll get 250t plus a constant. The other simpler way is to say if it's a constant rate, then we know that the relationship will be linear, so we just need to work out what the initial conditions are and we've got our value. Because it says the large container initially contains 3 liters of pure water and then contaminated water starts pouring in, we know that the initial amount of contaminated water is 0. Therefore, we can say that the amount of contaminated water at any given moment is going to be calculated by 250t if we're measuring in milliliters. We'll see later it talks about liters, so we've got to watch out for that as well. Maybe 0.25t, where t is the time in minutes and the volume we're calculating is measured in liters. The other standard assumptions, we assume the contaminant dissolves completely and that the water in the container is continually mixed. But we've also got this added complication that water is drained at a constant rate of 125 milliliters per minute. Now, the water being drained is going to have a varying concentration because the container initially contains pure water, but it's having contaminated water poured in. However, in this particular question, even the water being poured in doesn't have a constant amount of contaminant. The amount of contaminant in the contaminated water itself varies a bit. It looks like at the beginning, 5 minus e to the nothing, it's going to have 4 milligrams per liter. And then as time goes by, this e to the minus 0.1t term is going to shrink smaller and smaller. Therefore, the concentration within the water pouring in is going to gradually creep up closer and closer to 5 milligrams per liter. So that's an added complication. The actual amount of stuff coming in is going to vary, but also the amount of stuff going out is automatically going to vary because regardless of what's coming in, there is contamination appearing where there wasn't before, and what's leaking out will reflect the overall concentration of contaminant within the whole tank. The very first part of this question asks us to write down an expression for the total volume of water in liters in the container at time t. The fact that it says write down is an indication that it shouldn't be something that takes too much work. We know how much water there's at the beginning, 3 liters, and we're told how much water goes in and how much water comes out every minute. So this is designed to help us. We know that the amount of water in at the beginning is 3, and that every minute that goes by, another 250 mils is put in and 125 mils is taken out. So we can incorporate those 2 rates, the rate of increase and the rate of decrease, put them all together, and that's why they expect us to be able to write this down all in one go. So that should be our answer for the first part, and it's there for our benefit because it'll make it easier for us to answer later parts of the question, so don't forget why that's there. Hence, show that the amount of contaminant in the container can be modeled by this differential equation. Now, instead of trying to work backwards from this one until we've got somewhere, it's best to start from what we know. But if you get stuck at any point, look closely at what you've got and what they're asking you for and see if you can find the connections. We're interested in the amount of contaminant, which is measured as M. And what we have so far is the volume of the tank. Now, the amount of contaminant is going to depend on a few things. We need to think about where contaminant is coming from and where it's going. So dm by dt can be found by considering what causes M to increase, what causes it to decrease. Now, what's causing the increase is quite obvious. It's increasing because contaminated water is pouring in. We know how rapidly it's pouring in, 250 mils a minute, and we also know how much of that water is contaminant. So for every 250 mils of water, we're going to get a quarter of this number of milligrams, because this is the number of milligrams per litre. In fact, you can straight away see where this bit comes from. But essentially, that 5 minus e to the minus 0.1 t over 4, that is the increase due to the contaminated water pouring in. 5 minus e to the minus 0.1 t times 0.25. Since the concentration is this, and the amount of water pouring in per minute is 0.25 litres. The decrease, due to the water leaving the tank, well, we can start with the fact that there's 0.125 litres, but then how much contaminant is there? What is the concentration, I suppose, in here? Concentration of contaminant in the whole tank. To get that, we need to know two things. The concentration of the contaminant is known as M. That's what they've defined it as. But then the tank has a volume of V, and V changes as time goes by. So we have M over V times 0.125. Or I suppose we could write it as M over 8V. Now we just need to identify V. But remember, that's what they told us to work out in the first part. So they did this to help us out with this section. So if we've got M over 8V, then we just have M divided by 8 lots of this, which if you simplify it down becomes M over 24 plus T. And if we look up here, we'll find reassuringly not only the 5 minus e to the minus 0.1 t times 0.25 term, but also this term. So that helps us see we've got it on the right lines. Combining the increase, decrease, we get dm by dt equals 5 minus e to the minus 0.1 t over 4. That's the way they've written it, so I'm going to write it the same. Minus m over 24 plus t. I've justified where those have come from, so this is fine. That's the first 4 marks. So that's the bit I think that is different in every question, to a certain extent at least, and you need to look very carefully at what's being measured where. The next part should feel a bit more standard. We're solving a differential equation to find an expression for the amount of contaminant in milligrams, that was M, in the container t minutes after the contaminated water begins to pour in. So we need to solve this. And the first thing to notice is that this differential equation is not a variable separable differential equation. In other words, we can't pull apart the bits involving M and the bits involving T. We could have done if this had been the only thing involved, but because the concentration of the water pouring in is changing as time goes by, this makes this equation more complicated. But it is still a first order. If you are dealing with a first order differential equation where the variables are not separable, this level, that means you'll be dealing with an equation that you can solve using the integrating factor method. So we have something that looks like this. In fact, you might even consider rewriting this as 1 over 24 plus t times just so you can see more clearly that it is in the appropriate form for the integrating factor. Now, it's not essential to use integrating factor. You might find that just with a bit of savvy multiplication, you can see an easy way to turn this into what's known as an exact differential equation, where you can straight away pull apart the product rule situation. However, there's no need to do that if you are comfortable finding the integrating factor. The integrating factor is equal to e to the power of the integral of the term in front of m in this case, so 1 over 24 plus t. And because that integrates to ln of 24 plus t, and the e and the ln cancel out nicely, we know that we need to multiply everything by 24 plus t. So this entire differential equation will be converted into 24 plus t, goes in front there, perfectly cancels out the 24 plus t there. The added complication over here that you must not forget is that 24 plus t now appears as a factor on the right. The next thing to do is integrate. So we can integrate both sides with respect to t. And on the left-hand side, that's really straightforward. We get 24 plus t times m because we're essentially doing the reverse of chain rule. You can double check that you've done things correctly with the integrating factor by making sure that this thing differentiates to give the thing in front of m, which you can think of as 1 if you like, and that m differentiates to give dm by dt. So this is uv dash plus vu dash when uv is this. On the right-hand side, we have an integral to deal with. The integral is not the most straightforward one. It's going to take a little bit of work. It's time consuming, I think is how I describe this, as opposed to actually really tricky or sneaky. So it's one that you'll be able to work with. I would suggest pulling that quarter out to start with so you can see what you're dealing with. And then you'll be able to make some headway with this by first pulling things apart a little bit. So let's expand these brackets and see what we're dealing with. 5 times 24 is 120, minus 24e to the minus 0.1t, and then plus 5t, and finally this is the term that's going to cause us the greatest headaches, t e to the minus 0.1t. Most of that can be dealt with quite easily. In fact, you might even choose to do that, to actually integrate most of these terms. So the 120, for instance, when you integrate that, it's going to give you 120t. So I'm going to call it a quarter of 120t, so I've dealt with that bit. The 5t over here, I can integrate as well. That'll give me 5t squared over 2. The e to the minus 0.1t, that's an easy one to integrate as well. Don't forget the minus 24. E to the minus 0.1t integrates to give e to the minus 0.1t divided by minus 0.1, the derivative of the power. But divided by minus 0.1 is the same as multiplying by minus 10. And we've already got a minus 24, so this turns into a positive 240. Now that bit is gone. We can even pull out this minus sign and say all I need now is to take away a quarter of this integral. And we can deal with that integral using integration by parts. It's a classic integration by parts thing. So I'm going to rename a new integral so I'm not complicated by minus signs or fractions. I'm going to say let I equal this, and then we're going to use integration by parts to deal with it. In general, for integration by parts, we want to make sure that we choose for the thing we're going to differentiate the term which will simplify, that will reduce down to something nicer. So we'll normally, if there is, say, x e to the x, we're going to take x to be u, in this case t. The only exception to that is when you have ln involved, in which case ln is always the thing you differentiate, because the integral of ln, even if you remember it, and generally I just reproduce it by parts, the integral is more complicated than the thing itself and gets you in more of a muddle. But we have u and dv by dt e to the minus 0.1t. That's going to give us du by dt equals 1 And v, the integral of this, remember, we'll still get e to the minus 0.1t, but we need to divide by the derivative of minus 0.1t. So that gives us minus 10. That means that the integral that I've already helpfully labeled I up here, this is going to be equal to uv minus the integral of v du by dx, or in this case, v du by dt. So uv is minus 10t e to the minus 0.1t. And then we have to subtract the integral of v du by dx, which is minus 10 e to the minus 0.1t. A couple of quick things we can do right at the start. There's a minus inside, there's a minus outside, so we can turn that into a plus. We can also, if you want, take out the 10 so that we're not complicating things by that. But this should turn it into something quite nice for us. So my integral becomes, well, e to the minus 0.1t integrates to minus 10 e to the minus 0.1t. But we've already got a 10, so we end up with a minus 100. And that integral is what we're going to need up here when we come back to the original thing we were trying to work on. So this, if you recall, was the solution to that differential equation. And now we know this value. So this thing has turned into this. Oops. So we can replace that integral with this thing that we've just constructed. And now we have a bit of work to do. Of course, instead of taking away a quarter of it, you can add a quarter, and we can turn those negatives into positives. That will make life a little simpler. And we've got a bit more work to do on that right-hand side before sorting out the 24 plus t. There is one other thing that when I first did this, I forgot and it messed up the rest of the question. You need to remember not to forget this one. It's hard when you've got various other bits and bobs going on. We've got an integral here, and it's perfectly fine if you're doing an integration by parts as part of a greater thing to not necessarily include a plus c. But at the very end, when you've got the integral of the left-hand side and the integral of all the bits of the right-hand side, you must have a plus c at the end there. That's going to be really important. We'll use it in a moment. We'll find the value of c that corresponds to our particular situation. But if we don't have it, it's going to mess things up. Now, we're going to work through this. We've got that quarter. That's everywhere in here, so perhaps it'll be easier for me to write that as a 4 there to start with, and then all I need here is all these separate terms. We've got the stuff in this bracket, and then we have the stuff in this bracket, a quarter of each of those things. And so when I deal with a quarter, I sort all of that out. We've still got this plus c, but now I don't really need brackets in here anymore. That c has been multiplied by 4 as well. So if you like, you can just call it something else. It's not always necessary to explicitly say let k equal 4c. It's just some constant. We're going to find the value of it in a minute. We want m in terms of t, so we're going to simplify this. But first, notice what we can combine here, what we can cancel or group together. And we've got a term here that involves e to the minus 0.1t. There's another term involving e to the minus 0.1t here. So these two terms can go together and give what looks like 340 e to the minus 0.1t. We've also got the t term, the t squared. We've got e to the minus 0.1t and t e to the minus 0.1t. So when all of that's sorted out and all said and done, we're going to end up with m equals this stuff on the top, 4 times 24 plus t on the bottom. Now is when we want to think about finding the value for k, c if you've still got c in there. But we know that the concentration is 0 at the beginning because it was pure water, it told us in the question. So now we can make use of that fact and say this means that 0 equals, now this may look daunting, but actually most of this will cancel out nicely. Remember, anything involving t or t squared is just going to go because we're putting in 0. Even t e to the minus 0.1t, that's going to disappear too. The 24 plus t on the bottom just becomes 24. And then the only bit that actually gives us a value is e to the minus 0.1 times 0, which will give e to the 0, which is 1. So we get 340 plus k over 4 times 24. And because all we care about is making that 0, we know that k has to be minus 340. And then we've got our value. We can finally write this, and instead of putting plus k, we put minus 340, and we've got it. There's a little simplifying we might do here. In fact, with this 5t squared over 2, perhaps you want to double everything on the top and double what's on the bottom. You might even decide that most terms divide by 2 apart from that one, so you're going to leave that as a fraction but sort out the rest. It's not strictly necessary to do anything with that, so unless there's a very good reason, don't bother. That gives us the mass of the contaminant at time t. And the next part of the question, so we've done the 8 mark of it, we've found an expression for the amount of contaminant in the container t minutes after. Then it gives us this, which is really helpful in fact. This final part allows us to check that we've done things right. After 30 minutes, the concentration of contaminant is 3.79 milligrams per litre. Now it's important to remember here, this is another thing that I messed up the first time I tried this. We're looking for the concentration in milligrams per litre. What we've calculated here for ourselves is the mass of the contaminant in milligrams. So this is where it can be helpful to write out for yourself the definitions and the units for each of the variables you end up using. V is the volume in milliliters, and M is the mass of the contaminant in milligrams. And then if you've got a concentration that's in milligrams per litre or something like that, you can see how to calculate it. Now, we can start by finding M when t equals 30. And we can do that using the calculator. It's a bit tedious, but it works. If we try here, 120 times 30 plus 5 over 2 times 30 squared plus 340 times e to the power of minus a tenth of 30, so e to the minus 3, plus 10 times 30 times e to the minus 3 minus 340. So far I've got the entire numerator, so I've got a number for that. Then I'm going to divide that whole thing by 4 times, open brackets again, 24 plus 30. 54 in there. I've got my brackets right, we press equals, and we got a number, 25.657. And if you're anything like me, you'll be a little worried because that does not look like the 3 point something that they wrote in the question. But remember the units and all will not be lost. We found the value of M in milligrams. We have not yet found the value of the concentration. This is where we need to look back at the earlier part of the question. In part A, I, they asked us to find the volume, an expression for the volume in litres. And now they're asking us something about the concentration in milligrams per litre. So we could really do with the volume in litres at this time. It's not just 3 litres because it changes all the time. So we know that when t equals 30, V will be 3 plus 0.125 times 30. We can check here. If we do 3 plus 0.125 times 30, we get this, 6.75. So now there must be 6.75 litres. And the final thing we can do is find the concentration, which we get by dividing the number of milligrams, 25.657, by the number of litres. You'll notice I didn't bother saving that 25 point something on the calculator because I'd already written it down to a sufficiently high number of decimal places. So here I'm just going to use 25.657 divided by my previous answer. And this gives 3.80. That sounds reassuringly familiar. 3.80 milligrams per litre. That's the concentration Now, the question specifically said, assess the model in light of this information, giving a reason for your answer. Now, unless you're feeling particularly picky, hopefully you recognize that 3.79 as a true value and 3.801 that we're getting from our mathematical model are remarkably close. Any discrepancy is going to be